the other questions.
Oh, the entire thing.
Yeah.
Okay.
No, not this one. I just really want to do that.
Have any questions, William? Oh.
We didn't go over everything, like every section yesterday. So we did.
Did we?
I thought we had a couple.
That's why I'm going over. So again, doesn't really matter.
And then the resistant ones,
Applications.
the loops. I want to go over that, I guess. We have 3 loops. I forgot exactly how to use
your stuff.
Yeah.
I feel like you used the one that has to do with project one and lens law. Yeah, those are really confusing, especially with defining the direction of talk.
Okay. We'll do some of that then also. You want to do workshop?
Yeah.
Let's start first. We'll just take a standard. He's going to ask you something. He's going to ask you a few loops. We'll do it with numbers this time, and we'll go through the entire thing, I guess. Is there the practice exam that you want to go over, or should we just go over any random one?
I didn't even look. Right.
All right.
Basically.
Might be one of the questions. Just let it.
What's up?
Yeah, I have a question.
Yeah, that's one. Should we go over that, or do you want to?
That's fine.
Yeah.
So I gave you 3 loops. Shouldn't need. R2 and R3 have a value on R2 is equal to ohms, R3 is 26 ohms, R5 is 5 ohms, and R6 is equal to 6 ohms. V1 is equal to 8 volts, R and V2 is equal to 24. Three currents already labeled for you. Write down the three equations that could be used to solve these three. Currents is not required. How much current? So the first one tells you to write down all the equations that could be used for these APs, right? Write down all the equations for these three currents.
Yeah, that's not.
All three currents, okay.
So I have a question before you
Yes.
proceed. I didn't mean that he did not designate the direction of the current. How is he, like, I would have expected I1 to go up. I know that is not a problem because it only show up in the sign, right? But then I've asked some questions where I put the direction of current in a different place, but I get a totally different answer because of the algebra with signs. Like the way I'm supposed to subtract, I had it. And that kind of like screwed everything up. I've done several questions. I mean, several.
Do you have the solution?
I have everything.
You shouldn't get a different answer if you just flip direction of the current. You can assume I1 is going the opposite direction, and if you get a negative answer for I1.
I mean, that's not the only thing. The other issue is that in terms of placing the direction of, say, voltage drop and voltage gain, also affects the algebra, that is the equation. Because, for example, say for V1, let's say this side is negative, then I continue off to that side and it's negative, right?
Again?
Yeah, that side is
This
negative.
side is negative, okay.
Then I move up, then make that side negative, the top part positive.
So you can follow multiple conventions. So we'll start with loops, okay? And we'll go over how to do them. First of all, this is how many currents do you have in the circuit total? He gave you 3, but in reality, how many are there?
Okay.
So this current, you have this current, you have this current, and technically you have this current, and this current. So technically you'll have, what is that, 6 currents? 6 currents, okay. So let's start with this one. For this node, all the currents going in, I2 is equal to all the currents that are going out, I1 plus I3, right? If you apply the same thing at this node, I1 plus I3, because they're going in, I1 plus I3 are going in, and some random current, you can call it I4, is going out, right? Right?
Okay.
Right? I1 plus I3 is equal to I4. I1 plus I3 is equal to I2. You realize that I2 is equal to I4. These are the same two currents, so that's not actually a new variable. That's already a current that's known. This is I2, right? Okay. Okay. But we still have a problem with these two. So you can take a loop here, and let's assume your current here is going in which direction do we want it? Up? Down? Let's do down. Let's do down. It doesn't really matter which direction it's going. So if you want to take down, we're going to take a loop here. Again, there are two ways to do the sign convention. You can either do, because when you're going through a battery, you can either say you're gaining voltage and you're going through a battery. If you're going in the direction of current across the resistor, you're losing voltage. That kind of makes sense physically. A lot of people follow a different convention, which is if you're going into the negative terminal, you write it down as negative. If you're going into the positive terminal, you write it down as positive. The same thing with the resistors. So which convention? Actually, I'm going to use the EE convention. So with the EE convention, if you have a resistor that has current flowing through it in that direction, since the current is flowing in that direction, current always flows from positive to negative, right? That means this is the positive terminal, this is the negative terminal. Current always flows through a resistor from positive to negative. It has no reason to flow from negative to positive. It doesn't want to flow from negative to positive. It's from high to low. Low is negative, right? So in this case, this will be positive, this will be negative. This current is flowing in that direction. using that convention, for this loop, we would write going into the negative terminal, it's negative V2. Going into the positive terminal, it's plus let's call this I5. Plus I5 R5 equals to 0. Oh, we have R5. So same thing. Going in this direction, plus minus. Plus I5 R4 equals 0. Right? So that's negative 24. This is actually just one equation, one variable. We can solve it straight away. Plus R5 and R4 are 5 plus 4, 9, times I5 equals 0. Yeah. So I5 is equal to 24. Right? So this loop is not dependent on any of the loops. The current in it doesn't depend on any of the current. If we had a resistor here, so the only reason we could do this simplification is because we don't have a resistor. If we had a resistor here, when you do this loop, you're going to have another current in your equation. You can't directly solve that equation. Because, I mean, try doing it with a resistor here. You're going to say, okay, this current times this resistor, and this current times this resistor. You're going to have two currents. This current is not the same as that.
How do you know that?
Current is only the same. We're always assuming that the current is the same if there's no node. Because at every node, the current splits. Right? This current is not the same as this. So this is the same as this, the same as this. Okay, so we're left with two loops that depend on each other and one node. This is our node equation we're going to use later on. Here we can write our loop equations. So following the same convention that we just talked about, current is flowing from positive to negative across the resistor. Positive, negative. Positive, negative. Positive, negative. Right? You take one loop equation in that direction. Start from here, for example. Going into the negative terminal, that's negative U1. Going into the negative terminal, that's negative R3, I3. Right? Going into the positive terminal, that's positive I1, R1 equal to 0. Okay, so for the second loop, we do the same thing. We can start from whatever node we want, whatever point. We can start from here. We'll just start from here. Same place we started before. So going across this resistor is going to be I2, R6, of course. Across this goes in a resistor. Minus D2, because we're going into the negative terminal, plus R2I2, because we're going into the positive terminal, plus I3, R3, going into the positive terminal, and plus D1 equals 0. So if you want to do this, first thing you do when you get that question is label your positive and negative across the resistors, depending on the direction of the current.
That's where I missed it up sometimes. Because like how you made that side positive and the other side negative. I could have changed the sign, making the top part negative.
If you're assuming that the current is flowing, you're always assuming that the current is flowing into the negative, into the positive terminal of the resistor. Because it's from positive, negative, from high to low. I'm just going to move this I2 is equal to and we can solve these three equations. Actually, let's just plug in the numbers. I'm just going to go ahead and solve the entire thing. Minus V1 is 8. So the first equation, the number is minus 8 minus R3. What's R3? 26 minus 26 by 3 plus R1 is 4. R1 is equal to 0. Our 6 again is
6.
6. 6 I2 minus V2, 24. Plus R2, 14. I2 plus R3, 26. 26 I3. V1 is equals. Okay, these are two equations. So if you want to use it, we'll just write it down in the form where we have I1s and their coefficients, I2s and their coefficients, I3s and their coefficients, in case you want to do it with a matrix. We talk about it. I1.
Isn't that what the EEs use, the noodles thing?
The what?
The noodles or whatever, what the EEs do?
Noodles.
I don't know. What, the
No,
Jay
else.
and Sri showed these something into a matrix.
Yeah, you can do that too.
Isn't that what they do?
That's what causes it. So the coefficients of I2 are 6 plus 14, that's 20. Oops. 20 plus 20. I2 plus 26. I3 is equal to, move it to the other side, that's 24 minus 8, that's 16. And here we just have I1 plus I2. I1 minus I2 minus I2 plus I3 is equal to 0. So we have 3 common in both equations, so we don't want to eliminate I2. We try to eliminate either I1 and I2. You can pick anything. So we want to eliminate I1, we'll solve for I1. I1 is equal to I2 minus I3. Plug I1 into here, plug this value into here. It's going to be 4 times I2 minus 4 I3 minus 26 I3 gives you 8. Right? So that's just collecting the terms. 26 and 4 is 30. I3 is equal to 8. And we already used this equation, and this equation. So these are the 2 equations that we use to solve. If you multiply this by -5, so I think by -5, it's going to give you -20 I2 plus 30 times 5 is 150. I3 is equal to minus 40. Add this to that, you're going to get I2's cancel out, 26 plus I3, 26 plus 150, and 76, and 16 minus 40, that's what? 20. You get 24 I3. Oops. I3 is equal to negative 24 over 176. I think it gives you the value of I3. It doesn't ask you to solve this in the exam.
Yeah.
In the practice exam, it just gives you the value. Is it the same?
No, he doesn't give you the value of the value of everything.
It gives you the value of one of them. So suppose that if the solution was negative 1.55.
Oh, okay. Oh, with that.
He just tells you to explain the negative value.
Okay.
Oh, yeah.
Yeah.
Okay. Okay, so that's, I mean, I'm not really going to focus on this thing, just on the concept, on how to write the equations. Because that's the important part. If you do, I'm going to say from the algebra, it's not bad. But do you understand this convention? If you want to use it, do you understand it? Okay. All right, yes.
We're kind of confused on torque between infinite, just wires of charge, because the equation for torque involves
Area.
area, and so there's no area for a line.
Torque between infinite and
So like an example would be they predict like one's going out of the board and the other one is going to the left, and they ask us what the force between them is and what the torque from one on the other.
So just perpendicular ones. Louder.
Yeah.
Yeah, but yeah.
Although for us, one was coming out of the board, so it's in the Z direction, but I guess this wouldn't matter.
One is coming out of the board.
Yeah. And the other one is going to the left. Yeah.
To the left.
Yeah.
Okay. So this one has current.
And yeah.
This one has current. I2. Okay. So you know why the net force? I mean, does anyone not know why the net force is? So the net, what's the net force on this wire? We're asked about this. It doesn't matter, but I mean, which wire are we asked about?
Oh, from I1 on.
On side two, okay. So the force on I2 is 0 because so the magnetic field from B. Okay,
Right.
so you're going out, right, out of the board. The direction of the magnetic field is going to be this way, right? Around it, right?
Mm-hmm.
Okay. So here you're going to have 0. And for every point, or for every segment here, you're going to have another one here that's negative force. That's why they, so IL, so IL cross B gives you your direction, and the other one is just taking something like that. Cross B, yeah. So for everyone here, there's one that's opposite direction, so it sums up to be 0. So if you write down on every small segment how much, the direction of the force. So what's the direction of the force here, for example? The magnetic field is going to look something like that. That's the magnetic field B. And cross B, right? So L cross B gives you a force in this direction. Is that right? Oh, no. B gives you a force into the board. Into the board, don't move it. Into the board here.
Wait, how did you get that really, really, really quickly?
Okay. L cross P.
Right.
You point your fingers in the direction of L and curl them toward the magnetic field. So curl them towards the magnetic field. Point in L. Yeah. So into the board. Here, you point your fingers in that direction, you curl them towards the magnetic field. Gives you opposite direction. Okay? So same thing here. Curl them towards the magnetic field, gives you into the board. Towards the magnetic field, gets you out of the board. Here, you have 0 force. So everything here is going out of the board. Everything here is going into the board. Into the board, so it's going to spin around this point. So the wire is going to spin like that. And here, to find the direction of the torque, you're just going to have to use R cross F.
And R is the direction of the current.
No, R is your remember if you have a wheel that's spinning, this is your R. So let's say you apply force here F, this is your R.
So then how do we know what the radius is going to be?
The radius is going to be from your pivot point. From your pivot point to the point that you apply the force.
Oh, okay.
From your pivot point to the point that you apply the force.
But that.
So R. So let's take this point, for example, you're applying force here, right? That's the magnetic field. The magnetic force, sorry, it's going into the board. This is your R. And this is your F going inside. So
Okay.
R cross F gives you a torque in that direction.
Okay.
So that's the direction of the torque. And it's going to be spinning that direction.
Sorry, can you do the R cross F again?
Can you do it?
You said R cross F.
R cross F?
Using the right hand rule.
Right hand rule?
Yeah.
I don't like this right hand rule. I like another one. Okay, so remember how you find the direction, remember how you find the torque on a wheel or something in physics 1, right?
Yeah.
You do R, which is from the center to the point that you're applying the force. And then you R from the center towards the point that you're applying the force. And then you curl your fingers in the direction of the force that's being applied. So on this wheel, if it's spinning in that direction, the torque is going to be inward. Or just F gives you whatever force drop torque. Here it's the same thing. Or cross F gives you torque pointing upward. Okay. Okay.
Yeah. We are also kind of struggling with motional EMF. There was a specific checkpoint question. It was with the generator where you have the rotating loop and then like a constant B field going through it. And
Is that on the practice exam or homework?
it was on a checkpoint.
Checkpoint?
Yeah.
Is that before Faraday's law or after? Before.
Right
Okay.
before.
So get to things. Anyone wants to ask a question before that? Like on something that's before any of this. After you finish, can you scroll up, please? Bless you. Okay. I'm just going to pull up the topic for smart physics. Someone had a question on RC circuits first? Someone having trouble with RC circuits? After yesterday. Okay. 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 We'll do an RC circuit.
Because there's like a
Do you have a specific one, Aaron?
I just suck at it.
All of them?
I guess I can learn this back. It doesn't look too bad, but the ones in the homework, I don't know, I was kind of struggling with it.
Okay. Let me just go up and RC circuit again before that.
You want the one from practice yet?
Is that an easy one?
It's like 32 points.
Is it easy, though?
Which practice?
I mean, I think at them, so I
Which
can't say
one?
it's easy.
Which practice?
They give answers for.
Also
Yeah,
answers
I
one.
want to do it.
It's. Which one do you then?
I have no practice.
You said there's nothing. You said this isn't too bad?
I didn't think it looked too bad, but I didn't try it
Either
yet.
two.
But we also had the solution.
Or CS3.
It's the general one. I mean,
The other one's a little more complicated.
we'll have two capacitors. We'll just do the same thing with two capacitors instead. This was actually, I think, oops. This is similar to one on the whiteboard. On the whiteboard. Oops. So the capacitors are exactly the same. This is your switch. R1, R2. Also give imaginary values for them. Okay, B is equal to 9. This is equal to 3. This is equal to 12. 4 is equal to 8. And C2 is equal to 8. Sure. Okay. And we'll ask everything. So T equals 0, switch is closed. We want to find I, and we'll just say I is, or we'll find all the currents. So at T equals 0, we close the switch. What happens? We're assuming that the capacitors are uncharged before the switch is closed. So what, the capacitors act like a wire, right? Capacitors are wires. So we want to find this current. How do we find it? Which resistors do we have to take into account? These two? What about this one?
All of them.
All of them, right? So this is in parallel with this. It's going to give you 1, 2, 3, 12. over 4, 3 ohms. So that's just 12 parallel with 4, so it's equal to that. And 3 plus 3, which is 3 series with
So what's just
3, which is equal to 9. This is our equivalent of the entire circuit. So you can redraw the circuit if you want to. This is 9. 6. Volts. Okay. So the current I total is equal to 9.
Yes.
9 over 6, which is equal to whatever that is. We'll just give it 9 over 6. Okay. Can you all see that? Okay. So this is 9 over 6. And we were asked about, let's say, this current. So this current is going to split. Part of it's going to go into here, and part of it's going to go into here. Okay? Now, when we combine these two, we implicitly simplify these two into one resistor. So we can redraw that circuit. This is 3 ohms, and this is 3 ohms that we got from combining these in parallel. The voltage across this is the same as the voltage across this, right? When we combine resistors in parallel, the voltage across the resistor that we get is the same as the voltage across each one of the original ones. So we find the voltage across here, which is going to be the current. E is equal to I R. So the current that's flowing through, we just found it to be 9 over 6. 9 over 6 times the resistance, 3. It's going to give you 9 over 2 amps. Oh, volts. 9 over 2 volts across this. So we also have 9 over 2 volts across here, 9 over 2 volts across here. And again, V is equal to IR. We're trying to find the current. So I is equal to V over R. From this current, we have voltage across the resistor, and we know its resistance. It's going to be the voltage 9 over 2 divided by, which is 1 over 12. Divided by 12, and multiplied by 1 over 12. 9 over 24 amps. So that's for this current here. That's right when we close the switch at t equals 0.
That's current.
Yes.
Oh, that one in the middle.
Yes, that's correct. Any questions on this? Yes.
the 9 over 6. We got current 9 over 6.
Yes.
What was that?
This was this current here.
Okay.
So we first simplified these and found the equivalent resistance, which is this. So this current is the current flowing this. This is the current that's exiting the battery. Okay. So in this case, it's the same here, here, here. But after that, it splits. It's different. Okay. I'm just going to erase this. Okay, now we close the switch. And after a long time, what happens to the capacitor? It changes to infinity.
So tag this open circuit.
So if he asks you, if he says instead of t equals infinity, he wants to manipulate the question and say t equals 10 seconds. You can, but most likely this is going to be infinity. Because your time constant is usually really, really small. Okay, so, I mean, one of the questions in the practice exam is constant equals 1.5 seconds. That's big. That's really big. Constant is really smaller than that. Much smaller than that. Even if it was over 5 seconds, this would be really close to infinity in terms of e to the 1 minus e to the negative 0 itself. I mean, I don't know if he's going to ask you to approximate it, but so never mind. Never mind. Forget what I said. Okay, so at t equals infinity, what happens to the capacitors? Fully charged, right? What does that mean? Short circuited? Open circuited.
But then, is it a shorter, doesn't it just go through the others?
Yeah, so it just goes through this circle loop. Current needs a closed loop to flow. There's no closed loop, there's no current. So here I is equal to 0, right? And this is no longer valid. Here I is equal to 0 now, right? And if we want to find this current, we do the same thing. 9 over 3 plus 12. This is 9 over 15 amps, right? Any questions on this? How we got it? How we got 9 over 15?
Would the voltage across C1 equal the voltage across C2?
Has to be, doesn't it? It's an equal value in this case.
Oh.
Right? So now we get to that. So let's just keep this in mind, 9 over 15. This is I1 at infinity is equal to 9 over 15. 15 inches. Okay, so now they say we're going to open this switch. What's going to be the current through this branch right after we open the switch? To find the current, what do we need? What do we need to know to find that current?
The voltage of the capacitor.
Voltage of each capacitor, right? Or the voltage of the two capacitors combined. There's no reason to know which one of them. So how do we know the voltage of the capacitors?
Send the branch and the other branch.
So the voltage across here, and the voltage across the capacitors. This resistor does nothing in this case. This resistor here, since I is equal to 0, the voltage across the resistor, which is given by Ohm's law, IR, I is equal to 0, therefore V is equal to 0. So there is no voltage drop across the resistor. So the voltage from here to here is the same as the voltage from here to here plus here to here. Right? Okay. So actually, let's not do 8. Let's do 8 and 6. Let's sum them in value. What do we do now?
Multiply 9 over 15 times.
Right. So yeah, let's first find the voltage across here. Let's call this dB, whatever that means. dB is equal to 9 over 15 times 12, which is 4 times 4 is 36. 5 volts. So the voltage here is 5 volts. Okay. Now what? Remember, we were asked about the current here after we open the switch. So after we open the switch, okay, now we have the voltage. After we open the switch, we don't care about this branch at all. This branch is open circuited, so there's no current for it. So all the current that is, all the charge that's stored in the capacitors originally is going to flow out of the capacitors, right? Okay. But there's two capacitors. How do we deal with two capacitors?
Isn't the voltage the same? So
They're not the same values. If they were the same values, it would be the same. So each one would get half of that value. But they're not the same. But we don't care. Like if we combine these two capacitors, so we know that the voltage across the first capacitor plus the voltage of the second capacitor is equal to 36 plus 5. We don't care how the voltage is distributed because they're still going to be in series. So you combine them into one capacitor, you don't even have to find its capacitance. So we'll just combine these two into one capacitor. Voltage across the first plus the voltage across the second is equal to 5. So your circuit just becomes 1 capacitor that has a voltage of 36 over 5 volts across. And there was a 4 ohm resistor somewhere here. It was in series with a 12 ohm resistor here. And there was some stuff here that we don't care about because it's open circuited. Right? Remember the direction that the capacitor charged? Current was flowing into here, so this was a positive terminal. And this is still a positive terminal. And now, right after you open the switch, the capacitor is going to act kind of like a battery for the first few moments. So it's going to be pushing current from its positive terminal. So that's the direction of your I. So let open. And I open, it's just going to be 36/5, which is the voltage, over the resistance. So 1 over 12 in series, right? Right? Why are they in series? Because they have the same current flowing through them. Series means same current. Parallel means same voltage. Okay. And now that's your current. That we get for that. If he asks you at t equals 1.6 milliseconds after you open the switch, you just use this as I max. Because remember, I of t, after you open it, I of t is given by I max times e to the negative t over tau. Right? What's your tau? How do we find tau from this circuit? Or C. Where C is 1 over C1 plus 1 over C2 negative 1. Because remember, these were two capacitors. This capacitor was originally two capacitors in series. And the way we add two capacitors in series is 1 over C1 plus 1 over C2 to the negative 1. So you find your tau, and your equation is also. This is your I max. I max is the maximum current, which is right when you open the switch. Yes.
Why can you, so when you find the current, when it's open, why can you just add the 6 plus 8 to get to, the total capacitance?
We're not adding
them.
We're not adding 6 plus 8. We're adding the voltage across the 6 capacitor plus the voltage across the 8 capacitor.
Okay.
So if you have a line of whatever, a line of one piece, you have the first one key here, and the second one key here. The first one key has a voltage of 5 volts. The second one has a voltage of 12 volts. You don't know if your one keys are capacitors or inductors. They can be anything. They can be resistors, whatever. You want to know what the voltage from here to here is. The voltage across the first one key plus the voltage across the second one key.
Okay. Thank you.
Okay, appreciate it.
So IMAX is like the current right after you open it,
Right after you open
after
it.
a long time.
Because it's going to start decreasing, right?
Yeah.
Imax is, since the function is completely decreasing, and for all t, that means its maximum is at t equals 0. Because it's going to look something like, what, like that? Not like that, yeah. So this is Imax. Right? Okay.
And how do you find the maximum?
We just found Imax. So Imax, we found it by knowing the voltage across the capacitor right after you open it. And that voltage over the resistance of the loop, effective resistance, which is the resistance that you actually deal with. We don't care about this resistor out here because it's open circuit. So the voltage over that resistance gives you the current. And that's your starting current. After that, the current decrease. Okay.
So the voltage across the capacitor is Vmax, right?
Yes. They can ask you the voltage at any time. Instead, they can say, find the voltage at time equals t 1.2. You just use the same thing. Vt is equal to Vmax e to the negative t over tau. This is completely the same thing. Vmax, so how do we get from this to that? We just divide this entire equation by r. Right? R is constant for both of them. So V over R gives you I, Vmax over R gives I max. And we went from the first equation to the second equation. Right?
Yeah.
If they ask for what? They can ask for, just say, is equal to CB, right? So, multiply by C. This entire thing is Q. So So QT is equal to Q max e to the negative 2 over top. This is after you open it. So after you open it, all three graphs look the same thing. Let's go with V, I, and Q. All of them are decreasing. Right? This is after you open it, when it's discharging. When it's charging, V is increasing. Q is also increasing, but I is decreasing. Right? So this is given by 1 minus e to the negative 2 over tau times V max. This is given by Q max times same thing, 1 minus e to the negative 2 over tau. And this is given by its derivative, but we don't care about that right now. I e to the negative 3 over tau. I max, right? Where I max is the starting current of the thing. This is in case it's charged. This is discharging.
Well, for the charging point, you said it's the derivative of.
Yeah, because I mean, you don't even need to know this, but for this course. So dq by dt, d by dt. So that's going to be I is equal to d by dt. So if you find the derivative of the voltage function, this, you're going to get that. Okay. Okay. Is that good? Are you sure? Okay.
Is there anything before magnetic, motional EMF? I don't think there is. Is there? 11. Oh, there's magnetism. Or magnetism. How's magnetism? This thing, charged particle moving in a magnetic field. Not too bad.
Can we just go over one?
Okay. So it's charged particle moving in a magnetic field. The only thing they can ask you, we'll just go over a conceptual problem. Actually.
This may be, I think one of these is. A1 is equal to B2, which is equal to B3. So this is charge particle 1, charge particle 2, charge particle 3. Masses are also the same. Masses are the same, velocities are the same. The only thing that's different is Q. So compare, oops. Compare the magnitudes of Q1 and Q2, and compare the charges on the three particles. And what are the charges on the three? So magnitude-wise, which is bigger? Actually, let's do the charges first. What's going to be the charge on particle number 1?
Will that be an electron?
Electron.
Is going, because if the magnetic field is going this way.
The magnetic field's inward, right?
Yeah, so it would be going.
It would be going V cross V. You're crossing V with V.
So wait, what's the what way is the V vector?
V is this initial direction.
So you're doing this.
So that's for
V cross
So that'd
V
be positive.
to
Oh,
F,
okay.
right?
So
In this case, F is in this direction. Since it matches the right hand, therefore Q1 is positive. What about Q2?
Is it neutral?
Oh, this is a straight line. This is supposed to be a straight line. Label it as straight. Okay. Let me the
We need to do that last year.
sign of the chart on this.
0.
Well, it may have a charge, but it may have a magnitude, but it's uncharged. I mean, there's not positive or negative. It's neutral. Okay, so neutral charge. Uncharged.
Is the X indicating the direction of the magnetic field?
Yes. X is the direction of the magnetic field.
And then the arrow points to the velocity, right?
Yes. So the starting velocity, yes. The velocity at any moment.
Okay, what's the charge on the last one? Negative, because it's given. So you can try the right hand rule first. It doesn't work. Left hand rule gives you the right direction. It's not expected to be here. This is negative. Magnitude-wise. Magnitude-wise, which is bigger, this or this? Yes. R is equal to mv over qb. Did you have a question?
What?
I'll feel bad if I don't answer your question.
Yeah, I did. But
We're taking notes. We only have to leave in 10 minutes, but
Okay.
yeah, it was just about that generator.
Okay.
But it's fine.
My bad.
That's okay.
All right. So R is equal to mv over qb, right? So which one has a greater radius? 3. This is the radius of 3, right? So something like that. That means which Q is bigger? Q1. Q3.
Why is Q1 bigger?
Because its radius is smaller. And B is equal to Q over B. Right?
Okay. Forces and torques. Do I have a question on torques? Who had a question on torques? Did you have a question on torques?
Yeah.
Yes?
Hey, Basil.
Yes.
For the middle one there, in that last example, why or how do you get that one to be straight?
Either charge 0 or I guess there's
Charge 0,
a uncharged.
Can't really do the right hand.
Charge. Yeah, I mean it's straight. Charge 0. It's charge 0.
And then for the right one, so like if you use the right hand rule, or if you use the right hand rule where like frost is going up, B field's going in, since you're pointing for the right for B3.
For 3, okay.
So technically your thumb will be pointing to the left then, so you know it's negative because it's going right.
And it doesn't match your right hand rule, therefore.
But thank you. So we get the velocity going straight, and then the B field goes in, so wouldn't it be to the left?
Well, if it was positively charged, yes. But there's no force on it. So it's not curving. Since it's not curving, there is no force on it. Right?
Yeah.
wait, how can you compare the magnitude of the charge if it's neutral because you don't know what the radius is?
I didn't ask for the middle one. Just
Okay. But is it even possible?
I guess you can suppose that this is Q equals 0. Because technically there's no such thing as neutrally charged.
Okay.
Okay, torques. How are you guys with torques?
Torques and forces. No? Yes, 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 yes.
Magnetic moment would be like over like the direction.
Of magnetic moments?
Yeah.
Okay.
And torque is like, what is it? What is torque again? R plus B or something.
I don't know if I did it right.
U cross B. Where mu is. And I.
Okay. Okay, so what do we want to do? Direction of magnetic moments.
Torque.
Forces and torques.
And what is the torque again?
It's like when it's turning right.
Direction of magnetic moments, I guess. So you have a this is I. That's the direction of I. Right?
This one would
Yes.
the magnetic moment be pointing downwards
What?
for the loop that you just
This is really, it's in the plane.
in the plane, right?
It's like this.
So would the magnetic moment, the direction of magnetic moment point downwards?
Point where?
Downwards?
Yeah. So yeah, so that's that. Really, that's beautiful things. I should just do it out.
Yeah, sure.
Oops. This is your loop. This is your current, and this is your magnetic field. B. And it's just simple. How much potential energy does this have? So find U. So U is not a vector. Find U, which is a potential energy, and the torque on the loop, and in which direction it's going to spin.
So I thought U was negative magnetic moment dot.
It's not a vector.
It's not a vector.
Okay, so how do we find this? We want to find torque. What do we do first? Torque is equal to R cross L or mu cross B. Mu cross B is way easier.
Yeah.
Right? So what's the direction of mu? Into the Lord. It was like that, right? Curl your fingers in the direction of the current. And your thumb is going to point in the direction of mu. Mu is into the Lord. So the direction of the torque. What's the direction of the torque going to be? So it's going to be mu cross B.
So it's going to be
Point your fingers towards mu, then moving towards B. This, right? So which way is the loop going to spin now?
It's going to go this to that the far or the
Remember,
right side is going to come up at you.
mu, it's not mu, not. Mu wants to align itself in the direction of B. Mu always wants to align itself in the direction of B if you let it go.
So right hand side is going to come up at you. So it's going to go.
So since mu is pointing inward right now, it's going to want to point towards B. So it's going to move like that. Right? Right. How much torque do we have on it? It's straight forward. I guess I should make. So all I do is 90 degrees. So to find torque is going to be B sine theta. What's theta in this situation? 90.
Is it the angle between theta?
Theta is equal to 30. Okay, let's say this theta is equal to 30. What's theta now?
30.
So this angle is the angle between B and mu, right? Mu is in this direction, B is in that direction. What's the angle between us?
You said the torque is 30.
He's pointing into the board, right?
U is pointing into the board.
So
What's in this plane?
the angle is between tau and B, right?
Between mu and B. When you're taking mu, the angle between mu and B.
Yeah, so it's
wait. It's 9.
It's 90.
But then what was the point of putting the 30?
But the point of putting the 30 is that you need to figure out the angle. Like angles in the exam.
Oh.
Like he's not going to give you when he says, okay, he's going to give you a problem that has theta equals to whatever. That's not always going to be the theta you use. Theta you use is based on the equation. This equation is mu cross b. So it's mu b sine theta, where theta is the angle between mu and b. Oh, yeah.
Fullest, what order is the equation?
What r is in the torque equation? R is the distance from the center of rotation to the point that you apply the torque. So in this, to the point that you apply the force. So in this situation, you're applying force almost likely here. You're actually applying one and one force. So if you're applying the force here, it's going to be this is going to be your R.
So, I'm trying to get this right. It means like, because I feel like yeah, just as you said earlier, that the angle you're given isn't always the angle we use
Yes.
for the equation, right?
The angle. If the equation is something cross something, it's always 1 cross 2. It's always between 1.
Yeah. So, like most of the questions about temping, it's either you add the theta to 90 or you subtract theta from 90. Or, I mean, basically, it's the angle between mu and b, right? That's the angle we use for calculating.
Yes.
But then, I feel like if theta, I mean, if mu is pointing into the board, right, this way, and b is pointing this way,
Mu is
and it gave us
pointing into the board.
yeah,
Mu is pointing into the board. B is pointing in this direction.
yeah.
That's not even meaning.
But yeah, that's amazing.
That question, that's some.
Oh, okay.
Because they're in different planes.
Yeah. Because I mean, it's entirely that.
Anything that's coming out of the board or into the board is perpendicular to the plane of the board. If it's coming straight out. Yes.
In the monkey example, the voltage drop doesn't matter if it is a capacitor or resistor.
Is that for either resistor or capacitor? Yes, because monkeys can be whatever. Some monkeys are capacitors, while others are resistors. Okay.
Question on induced EMF. On induced EMF.
Induced EMF, yeah. So I think the induced EMF is next, right? Induced EMF. Induced EMF is Weier's law is next. Any questions on Weier's law? Weier's law? Weier's law? Magnetic field from a wire? No. If you have any questions, please ask. Okay. So Ampere's law is next. Actually. Any questions on Ampere's law before we get into induction? Any questions on Ampere's law?
One thing I get.
It's the one thing you get. Okay. One.
Yeah, that one.
This one?
And then it ends up
This one?
equally PO.
Okay.
Solve for it. Unless the VPO.
I don't know if
Beautiful. But you would never
people on the things can see this.
That was, no, he wrote that email. He wrote for our last meeting, fair days. Remember last week we had to do it, something like that.
Okay. All right. Blah 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 blah. Words. Okay. So we want to find. What do we want to find actually? We need to know what we want to find. We want to find the potential. We're asking about the magnetic field at this point, for example. Okay, B. The magnetic field at B, the magnetic field at R, and the magnetic field at S. Okay?
we also want to find the integral from A to B, I think. So we want to find these. We want to find the integral from A to B of E dot L. And we'll also do the integral, the enclosed integral. We'll see that the enclosed integral. Okay, how do we find B? Does it give you the equation for every sheets of wire? There you go.
Isn't that the
He says
two?
equals 1/2 mu naught n over Li. I've never used that equation.
You never use that?
No.
You did this with Ampere's law? This problem?
I mean, I went to the ARC for it today and she didn't have me integrate, but I don't know if I did it right. Aaron will check.
B is equal 1 over 2 times 1.
Not N,
You know 10?
N, and L.
Yes, N over L.
And over L. Okay.
Yeah, times.
It's times L.
Where L is this length. No, there's no R. It shouldn't be dependent on R. It shouldn't be dependent on distance.
He's just asking the magnitude. If you're, I don't know if it's right.
Yeah.
Looks good.
Okay.
Like what I did was something here. So it's
This is just the number of eyes that are in here.
you
They're
gotta
just
wrap it around. So it's all like this. This one's also
That's just I.
I prime, which is total current. I mean, N over L is just saying, okay, so N over, in this case, N is equal to 13, I think it's 18. So 18 wires per meter, and you have M is equal to whatever length you have, L. So it's just going to be the number of, so one of the wires is carrying a certain current I1. The entire sheet is carrying N times I1 wires. Okay? That's what this is. It's just saying. If you want, you have to take into consideration all the currents. Or, sorry, the current. Okay. Alright, so we want to find the magnetic field here. What do we do? We can just straight out apply the equation. E is equal to 1 over 2 mu naught. N over L is equal to 18 meters. Which is times I is I1. Here's I1. I1 is equal to 2.9. So that's the B field from this one. It's going in this direction. We'll do this blue. It's going in this direction at this point, right? And from the other one, what direction is it going? The other sheet from this sheet. It's going out of board. Right? Out of the board, around. So out of board, around. Each wire is doing that, right? So at this point, it's going to be going down. So here, it's also going to be going down. Both of them are down. Okay? Okay, and we'll also do it outside. So outside here is also going to be going down. The other sheet outside is going to be going up, right? It's going right hand rule gives you that. So you go in that direction, right? And here.
You want to go up and down, up to the right one, down to the left.
Oh, this one is inward. Down to the left. Up to the left, right. So this is just saying that here you're going to add them and fill together. Here you're going to subtract them. Here you're going to subtract them. Okay. So for any B, it's given by this equation. B is equal to 1 over 2 mu naught, whatever.
So would you say R is
If you don't understand where this came from, this comes from directly from Ampere's law. If you take an infinite sheet, one infinite sheet that has wires, you can apply Ampere's law on it, same way we did Gauss's law.
are going to cancel out because the magnetic field is perpendicular to it when you do B dot dl. And here you're going to have B dot dl times this, B dot dl times this distance. Okay? So this distance is L, this distance is L, and this has N wires per L meters, and the current I per wire. You're going to have the integral along this path of B dot dl is equal to dot I enclosed. I enclosed is just going to be L times N over L, which is the number of wires that are enclosed in here. Okay? So you're going to solve for B. For this, it's going to be 2L, because one L is here and the other L is here. And that's how they got this. And we don't consider these. Yeah.
Why? So for the homework on this problem, you can use the equation to be 5 by 2 pi r. Why does it work?
You're not
This is fair.
Yeah, exactly. Let me double check, but I could have sworn when I.
That's what it's fair.
What unit is this from? Example. Maybe I saw. Sorry.
No, it shouldn't work because the magnetic field is in the end of the distance.
Wait, Basil.
Yes.
For this one, it says solve the integral B dot dl.
Okay.
Since B dot dl is equal to mu dot I enclosed.
Okay, we'll get to that. This was just where we got to the equation for the magnetic field sheet.
Oh, okay.
Okay. So now the integral, if you want to integrate.
Which one? This one?
So we want to integrate along this path. First we want to integrate from A to B. We'll just do first from A to B and then the integral along this entire path. So if we want to integrate from A to B, okay, it's always easier to take two paths. One of them is perpendicular to the magnetic field. Like, remember what we did with the sphere? When we had like a wire carrying current outside the board, for example, or that's inside the board, and we want to take from point A to point P, for example. What we did, instead of going this path, we split it into two paths. One that is always parallel, because the magnetic field is given by this green marker, in that direction, and so on. We took one that is parallel to the magnetic field, and one that is completely perpendicular to it, right? And the magnetic field here is like that. Oops, this is good. I'm going to change this side out. Like that, right? So this path is parallel to the magnetic field. When you're moving across it, you're moving it parallel, anti-parallel to the magnetic field. You're moving in the same direction, completely opposite. And when you're moving from here to here, you're moving completely perpendicular to the magnetic field. That's 90 degrees off, right? So that's what we simplify it, always. Because when you're moving perpendicular, it cancels out, the integral is 0. When you're moving parallel, your angle is either 0 or 100, 0 or 180. So the B dot dl is just simplified to B times L. It's not its cosine. Cosine 0 percent 180. We do the same thing here. If we're integrating from A to B, since the magnetic field in the region here is going to be going either up or down, right? So we split it into something that's parallel, that's up or down, perpendicular. The perpendicular one is going to be 0, right? This integral is going to be 0. So remember the integral from A to B. So the integral from A to B is equal to the integral from A to, let's call this C, A to C, plus the integral from C to B. C to B is perpendicular, therefore 0. A to B is parallel. So take the value A to B. Integral from A to B of B dot dl. Oh, B to C. A to C. Sorry, A to C. A to C. Of B dot dl
We don't have to do mu naught I enclosed. I mean, technically you can do mu naught I enclosed and take the entire enclosed surface and then subtract the value that magnetic field is more complicated because B here is not the same as B here. So in case of an infinite sheet, it might be easier for you to just integrate. You're not really integrating because it's constant. Okay. B dot dl, we can simplify it into B times L, B times dl, because we said cosine. It's going to be cosine of, in this case, we're moving from A to C, so cosine of negative 180, right? Because we're moving in that direction. Magnetic field is pointing in that direction, so this is your angle, theta. It's 180, so this should be negative B dl, right? Which is just equal to negative B times L. L is evaluated from A to C. L evaluated from A to C is just the distance from A to C, which is H. I assume they give you H, or they give you a weight, or I mean they give you enough information to find it. So that's just going to be negative B times H for your integral from A to B, which is the same as A to C, right? Okay, so now what if you want to integrate from A to B to C to D back to A? So this entire loop, I'm going to erase this.
The same thing.
So we want to integrate from A to B to D to C. We can do the same thing. We can do the same thing or apply Ampere's law.
Can we take charge of the symmetry, the fact that from A to B, maybe from C to D or from B to C, I mean, multiply by 2?
It's not going to be the same.
It's not
Magnetic
going
field
to
is
be
not
the
the
same. Because I feel like from B to C,
same. Magnetic field is not going to be the same.
I mean, I believe they will have like opposite signs, but the magnitude should be equal.
So B here, we would use the B we get from this and that, which is pointing in that direction. B here, the directions. One's pointing up, but there's down, so there's going to be less. The value is going to be less. Okay? So we go from here to here, or whatever direction we're going. It's going to be less. Actually, you can't use Ampere's law on this one. You have to do it this way.
Why can't you use it?
Because you have to consider both sheets if you want to do Ampere's law. If you want to do Ampere's law, you're going to have to separate two Ampere's law. Remember how we did Gauss's law? How we said if we have three charges, you can't just take and you evaluate the electric field at this point using Gauss's law. You can't just do this. You have to take one surface here that's symmetrical to this charge, another surface here that's symmetrical to that charge, another here that's symmetrical to this charge. This is the same thing. You have to take a path that's symmetrical to this sheet and another path that's symmetrical to this sheet. So if you want to do it at this point, you take, here's your path. At this line, I mean, here's your path. At this line, here's your path.
Why can't we use the the I enclose? I mean,
Because of this.
What?
Because of this. Because you can't. So, I mean, you're only considering one sheet. If you say mu naught I enclosed, you're only considering one sheet.
Yeah, but
there's also another sheet there.
That sheet that's within the trapezoid. The I1 is the only sheet that's within the trapezoid.
The only what?
I feel like I1 is the only. I mean, I1 is.
He's basically saying that I1 is the only one that's through the trapezoid.
Yeah. So why can't we use that to find?
Because you can enclose more charge in it, more current in it. I mean, you can manipulate Ampere's law the way you want to. Because if you could manipulate it the way you want to, it's going to be a different answer every time you do it. If you can manipulate it the way you want to, then you could just do that. And
Yeah.
look, you have magnetic field inside. You can't do that. So it has to enclose everything in this. You have to find a path that encloses everything in your system. Absolutely everything, all the currents in your system. Or I mean, a sample of all the currents. Because here, you're not actually going to enclose the entire sheet. You're just going to enclose a sample of the sheets because you know everything else in the sheet is the same. Because they tell you that 18 wires per centimeter throughout the entire thing. would be ridiculous to enclose the entire thing because it's infinite. So you just enclose part of it, and you know it's going to be the same as enclosing the entire thing. You're just going to have a bigger length.
I feel like if we use I enclose, or then the integral of b dot dl. So I feel like the dl is within that portion of the sheet, right?
Right, but you have another sheet that you're not considering.
But that's not within the trapezoid. It's not within the trapezoid. So
when you do this, you're only considering the magnetic field from the ones that are here. But in reality, so if this wasn't here, yes, you can do that. But because you have this here, you have to also consider this. So when you enclose something by a path, to do Ampere's law, if you enclose it by a path, you're saying, I'm going to find the magnetic field from this thing that's inside. Okay? And since you're not enclosing this, you're saying, I'm going to find the magnetic field from this that's enclosed inside. This is the only thing that's enclosed. So if you want to consider this, you have to also enclose this inside your path. Everything in your system has to be enclosing your path for your integral to be right.
Because I don't know, maybe because of a different. Because there was one question I think on the pre-lecture, the checkpoint, where it showed current carrying a current, the conductor carrying the current. One is within a sphere, another is not enclosed within. So they only use the current that's enclosed within the sphere to calculate the magnetic field. Yeah. The actually didn't bother the ones on. So I feel like
There's no way to enclose. Right?
Yeah.
And that's your take after that, right?
Yeah.
There is no way to enclose this entire thing with a path that's passing through this center, other than this. Because technically this is, instead of enclosing it as in including it, you're excluding it. So your path is typically reversed in this situation, right? So your thing has to be, so this is the only path that includes everything that's existing.
Yeah, I think definitely think the current density to, I mean, just the portion of the current that's within, say, our loop or
Right,
whatever.
because we want it at that point.
Yes, that's why.
We want it at this point, so we take it like that. This is everything contributing to the magnetic field at that point.
Yeah. Yes.
Do you guys have any questions? Okay.
Yeah, I think. So this is the B dot the L part of the question, right? Yeah, I think it is. Yeah.
Do you have any questions? Do you have any questions on this? Yes.
You did, where you were explaining the integral from A to C over here, how come you change this to negative? Where'd you get negative, or where'd you get cosine of 180 from?
Because B dot dl, your path L is direction.
Yeah.
Your path B is in that direction.
Why the B?
B.
Oh,
It's in that direction for both sheets, and now it's in that direction. So it's B dot dl. B times L times cosine the angle.
oh, okay. Yeah.
Cosine.
One last question. Actually, is 29. I mean, 9. It's right.
Actually, I'm just going to draw it, then you tell me.
Excuse me.
What they give you? Current? They tell you current is going in some direction.
Which one is this?
Or are we moving the loop?
Oh, yeah, I need help with something.
We're moving the loop.
What?
We're moving the loop.
Yeah, we're moving it. Yeah, that was.
We're moving it like this.
You want it?
Yes.
Basil?
Yes.
Yeah, I'll take it. Okay, we know R. Ohms.
Sorry. Oh, yeah, I'll just tell you.
Whatever. H. B.
Your outlet of the package increase. Yeah, 13 to C. So,
Magnitude of the maximum voltage induced in the loop of wire, and when does this happen? Okay. We have a conducting wire formed in the shape of right triangle with base. D is equal to 17 centimeters. H is equal to 29 centimeters. And having resistance R. From the triangle makes one complete rotation in time t equals t is equal to 2.0 seconds. It makes one complete rotation. One complete rotation. A constant magnetic field B is equal to 6.3 Teslas. It exists in the entire region where the wire is rotating. What is the magnitude of the maximum voltage induced in the loop of wire? And when does this happen? How does this time go? Okay, we'll just do the first one first. What is the magnitude of the maximum voltage induced in the loop of wire? And when does this happen? What is the EMF given by?
In a loop, isn't it?
EMF induced.
VBL.
Okay. Cross out, I guess. That's a more general one.
Sine theta. I mean sine theta. Oh, okay. You can see.
oh, yeah.
This is essential to life.
Essential to life professor right there.
Just look, so the one with motional EMF can be solved with Faraday's law. Okay? But motional EMF cannot be used to solve every Faraday's law problem. Because what is this? Okay, let's just stop for a second and go over Faraday's law. Faraday's law tells us the EMF, which is the voltage induced in a loop, is equal to the change in flux over the change in time. Okay? So if you have a loop, whatever loop it is, inside a magnetic field, we're saying that as the flux changes in this loop, the voltage is you're gonna have an induced voltage, okay? In motional EMF, we said you have a loop that looks like this, and we're just gonna move this, okay? We're just moving this bar. We're just moving this red bar from here along here. What's gonna happen when we move the bar? The area is gonna increase. When you move the bar, A is getting bigger. Since A is getting bigger, flux, which is getting bigger. Flux changed. Flux changed, EMF induced. You can get it. You can do the same thing with the equation that we just wrote down here.
B field increases because it's more.
B field increases. So flux increases because there's more area, so there's more B lines penetrating this place.
Yeah.
So basically, this is you use this when obviously you use it in a problem like this, but you use it when the B field's not uniform.
You use it when it's not.
No, wait. In this case, it is uniform.
You can use it when Faraday's law is not.
I think I'm gonna get mixed up with that other problem we had at home.
So
in this situation, you can either do V is equal to IL cross E. No, what is it? V is equal to. No, sorry, not V. The EMF is equal to VB cross L, which is so the velocity it's moving at. And how are you going to find the velocity? From the angular frequency, which you get from the time, which you get from whatever. And then using V, sorry, I need to write this down. VL cross E, right? Using V, you're going to have to find L. L is this length.
with the hypotenuse of the thing or the height? Or the height? I feel like it should
The
be
height is, it's pivoting around the height. So the height isn't technically moving.
So wouldn't it be B? Wouldn't 17, would that be L? Or no?
So the
No,
magnetic
it
field
should be B, right?
magnetic field is in that direction, right? And we're moving in that direction for B. So cross gives you 0. I mean cross, yeah, sine of 0.
I thought we were moving in this direction.
We're moving this direction. And at it's going to change.
Okay. Yeah.
But when it's here, sure, the angle is, it's going to be moving in this direction. The magnetic field is going to be out of the page, right?
Yeah.
So you're going to have a force that's up or down. Up or down. Still not going to induce anything because there's no charge separation, right? There's no charge separation, there's no charge induced. Remember, if you had this thing that's rotating like that inside a magnetic field, let's say it's into the page. These two parts don't do anything. Because sure, at some instances they are going to have a magnetic field, but when they do have a magnetic field, let's say it's one of those instances, when this loop is laid like this, okay? When this loop is laid like this, when this loop is laid like this, it's pivoting across that, right? Right? This one here, it's moving at a velocity like that. The magnetic field is in the page, so it's moving at a velocity like that. So it's okay like that. So this segment here is moving at this velocity. The magnetic field is into the page, so the force is pointing in that direction. But the other one's going to be pointing in this direction. But it's just a line. Just a line. So you're going to try to leave the conductor, but they're not going to be able to leave. It's just a line. As opposed to here you have a force pointing that direction or that direction. So they can walk along the line. This is why friction happens. Because they can move along the length of the line. The length of the wire. Instead of just moving this direction and that direction. No?
Can you explain for the top wire and the bottom wire? Which direction does that go?
For the top wire and bottom wire?
Yeah.
Well, at this instance, you have, let's say it's going to start rotating in this direction. V is going to be out of the page. Actually, we're not going to have any at this instance. Sorry.
There wouldn't be any velocity.
At this instance.
Or when it's like moving though.
If it's like this, and you want to go more in that direction, V here is going to be downward, right? Magnetic field is going to be into the page. Right? Sorry, V, magnetic field into the page, gives you force in that direction. So the force is in that direction. So charge separation goes here on these edges. That's the edges.
Positive charges go towards
the force. Yes, so the assumed current is positive. Okay, but we're not going to do this. I really can't find a reason to do it with anything other than Faraday's law. EMF is equal to chain negative d phi by dt. Negative sign is from that silly guy lens. So phi, the integral b dot dA, right? This is phi. This says that a change in phi can happen due to three things. In general, three things. A change in area, a change in magnetic field, a change in the angle between them. Okay? In this case, your area is not changing. Your magnetic field is uniform, therefore not changing. The only thing that is changing is the angle. Changing, yes.
But when the triangle's moving,
Yeah.
doesn't the magnetic field change then? Because it's going outside, if it's coming out of the page.
Magnetic field is uniform in the region. The field of the region.
field of region B is given by 6.3 Tesla, uniform magnetic
Oh,
field.
okay.
It's going out with the page. The flux is going to change. I mean, the flux is going to change.
Yeah.
So BA or angle between them. In this case, it's going to be the angle between them. Okay? So what your flux at any given instance? We can do that. We can find a function for flux. Let's. Okay? How do we find the flux at this instance?
B dot D A.
B is uniform, right?
Yeah,
A is uniform, not changing.
Yeah.
So that's going to be BA cosine theta. Phi equal to BA cosine theta, right?
Is theta 0 in this case?
In this case, theta is 0. But we want to find a function of time for the flux. So that when you find a function, you can manipulate it easier. So they say that in 2 seconds, the loop rotates. So an entire rotation in 2 seconds. So it does 2 pi radians in 2 seconds. In 2 seconds. Right?
Yeah.
That means omega, which is equal to radian frequency, the number of radians you go in a second, in 2 seconds. The pi. Pi is equal to omega in this case. Okay? That's how many radians you go every second. Right? Pi radians per second.
So we substitute theta for omega,
Omega t.
omega t.
Omega,
Oh,
again,
okay.
number of radians per second. Number of radians per unit time. Right? Solving this for theta gives you omega t. That means phi as a function of t is equal to b a cosine theta. Do you see how we got that?
Yeah.
Oh,
So we could have, I know there is a,
sorry, omega t.
could we have just used the omega VA sine, the sine of WT, because I know there, we already derived that for the first element. There was one, sorry. There was one related formula where we, I think, yeah, we could just have to like do the derivative of this one to get the phi.
Yeah, so for the EMAP.
Yes.
Yes, this is just a phi, this is just a flux. This is just the flux at any given time. Okay? The flux at any given time is given by this function. And we know that the EMF is equal to negative d phi by dt, d phi by dt. Okay? So how do we find this derivative? What's the derivative of this?
So the negative VA,
Negative dA
omega,
omega. The derivative of cosine is negative sine. This is a function
How did you get that?
derivative. EMF is equal to Faraday's law, because the EMF is negative d phi by dt. Phi dt, whatever. Negative d phi dt by dt.
Now, if you just memorize that, then you're good, right?
What is this?
No, BAW sign.
Why would you memorize it?
it's an equation.
Why would you memorize it?
In case you
What's the
forget how
problem?
this whole
Why?
system. You know?
You're always going to have one thing changing with time. Okay? And your system's going to describe it. Your system's going to say, your loop, the question that you had in class, your loop is moving at a speed like this. In this case, what's changing? Is the area changing?
No.
Is the angle changing?
Yes.
No,
The one with
this one?
the one with the wire
no, he's talking about the loop.
and a loop moving in that direction.
Oh, okay.
Is the angle changing?
Only the B field.
Only the B field. The B field through the loop, though.
Gotcha.
The B field through the loop is changing.
That's actually on the practice exam too.
If this one wasn't moving and your current I was changing, what's going to be changing?
your B field also. Because B is equal to mu naught I over 2 pi dr. 2 pi d. So multiple things can change. It depends on the thing that changes. You formulate your equation. When you have your equation, you use it to solve everything. This is our equation in this case. And now we can answer every question that he asks about it. He says, what is the magnitude of the flux of the maximum voltage induced in the loop of wire, and when does this happen?
How do you find voltage?
Yeah, man.
This is like the school term.
So that would be
Yeah, I was confused.
Magnitude of the maximum voltage induced. We want to maximize this. When does this maximize?
when sine omega t is 1.
1. Sine omega t is equal to 1. That is, omega t is equal to 90 or negative. Right? Or let's do it in terms of.
What is negative?
Let's do it in terms of radians. Go ahead.
Oh, okay.
Pi over 2 and 3 pi over 2. Which is the same as negative 90, but other way around. So pi over 2 and negative pi over, and whatever, 3 pi over 2. When omega t is equal to that, right? So t is equal to 1 over 2 and 3 over 2. Because we're solving omega. Remember, omega was pi in our situation. We solved for omega up there. We said omega is equal to 2 pi over 2, right?
Yeah. So omega is pi.
Which is number of radians you go in the amount of time they're given. Amount of time is 2 seconds. So 2 pi says you go entire rotation in 2 seconds. So that's 2 pi radians in 2 seconds. 2 pi over 2, that's pi. So you get t is equal to 1 over 2 and t is equal to 3 over 2. This is a comma. Gives you maximum EMF. Let's calculate the EMF of that situation.
Would you just want the seconds, or would you want us to calculate it as well? Just answer.
Okay, in this situation we got like this. Yes, what?
Oh, I was saying that, would you want to calculate it as well, or would you just want the t?
He wants you to calculate the magnitude of the maximum thing.
So,
So it's just going to be a omega. Okay, so just a second. In this situation, all right, remember this condition. We said at t equals 0. We said at t equals 0, theta is equal to what? 0. Theta is again b. It's b in a yes. Well,
we have to say 0. I'm assuming it's
0. Because it's the angle between B and A. And you can assume your angle A vector in whatever direction you want here. Theta is equal to 0. Okay, yeah. So in this situation, it was at t equals 0, theta is equal to 0. What if the question asks the exact same thing, but the triangle started out in this position?
90.
At t equals 0, your theta would be 90, right?
Yeah.
Therefore, your flux function would have to be sine. Your flux would have to be sine to satisfy that. Or cosine plus or minus 90, depending on the situation. Because your function has to satisfy the initial conditions, right? The initial condition here is t equals 0, theta is equal to 0, right?
So there's that. Okay, let's say
If it started out like this,
yeah.
This is your area vector pointing in that direction. This is your B pointing in that direction, right?
Yeah.
So there's a 90-degree difference between the two.
So that means flux is 0 then. Because 90 is
Yes, flux is 0 in this at the starting location. Yes, it's 0. But it would be described with BA sine theta instead. So this would be BA sine omega t, and your derivative would be BA omega cosine omega t.
Oh, why would that be the case?
Because you're starting at this location. You're starting in this situation.
Why would you change the sign? Like,
What?
Why would you change the sign though if it's down
To satisfy the initial conditions. Go ahead.
So the idea is to keep the induced, the flux
to keep your equation, sorry, oops, it's disgusting. To keep your equation, I'm really hydrated. I've been talking for hours. To keep your equation, the idea is to keep your equation consistent with the system that you have going on. Your system says that actually it doesn't even tell you anything about the initial conditions. Well, it just says a conducting wire formed in the shape of a right triangle with base b equals 17, whatever, is done with this. So I guess you can assume initial conditions. But let's assume the problem tells you this is how the loop starts out. It starts out like this, right? And it's going to start rotating in that direction. Okay? This is how it starts out. So it starts out with an angle of 0 between B and A. At t equals 0, the angle is 0. B, A cosine omega t satisfies that. Because at t equals 0, omega t is 0. Okay, and you have maximum flux. If it's said that you're starting out in this situation, at t equals 0, you're here. Okay? If you're at t equals 0 here, at t equals 0, your theta is actually 90 degrees. Right?
Yeah, that's true.
Right?
Yeah.
So, at t equals 0, your theta is 90 degrees.
So we
You can
use
either use cosine of omega t plus 90 or sine.
It'd be omega t plus 90. If you do,
Omega t plus 90.
what would be plus 90?
Because at t equals 0, one angle would be 90. So at omega t equals 0, omega t is 0 plus 90 is 90. So,
oh, okay.
which is the same as sine. I mean, when you're using sine instead of that, you're just switching to a different angle.
Yeah.
You're actually switching to a different angle instead of using the same angle, but it's the same value. Mathematically, it's the same.
Well,
But he doesn't actually put in constraints, so I'm sorry. I thought he told you it starts out like this, but he doesn't say that. He just says it rotates like that.
so I know he said that every time, I think this is about induced current or induced EMF within a loop, right? He said if the initial constraint is that the magnetic orient towards this given direction, then the induced EMF would make sure the induced EMF within the loop will also orient the field in that initial direction. And as a result of that, the direction of current would change just to keep the initial
That's
direction.
Lenz's law, right?
Yes.
That's Lenz's law.
Which applies here also. But I mean, it's the same environment, but a different question. Same environment that you have going on. You have a loop that's going to change its flux. Okay, so all of them are related. Lenz's law. Well, let me just finish this problem. Okay. B A omega c whatever. So he says when is the EMF maximum? EMF is maximum when this function is maximized. This function is maximized at these, right? When that happens, and at these angles, omega t. That means when your area makes an angle of 90 degrees with your magnetic field. That means your triangle is in the direction of the field lines, right? Because the area vector appropriated to the triangle. So this is what your triangle is like, and this is what the field lines coming out of the board. That's when you have the maximum voltage. But minimum flux. Is that if it's cosine of 90 or pi over 2, 1 over 2 times pi, it equals 0. 0 flux. And you can see it's 0 flux. There's nothing penetrating it, right?
So if flux is 0, voltage would be
Maximum. Yes. So one of them is the derivative of the other. In this case, one of them is given as cosine, and only for something that's rotating. Okay. Only that's for something that's rotating. In that loop that's moving, you don't know. In that loop that's moving, it depends on the functions. So one of them is a sine, and the other is. Let's start from here. And the other is a cosine. Maximum, minimum, maximum, magnitude-wise, minimum, maximum, etc.
When one is max, the other is min. In the situation of a rotating loop. This is the way the function is. Okay, how does the time for max voltage compare to the time for maximum magnitude flux loop? I guess I don't know what exactly he's asking here, but how does the time for maximum voltage compare to the time for maximum magnetic flux through the loop? So you have to have initial conditions to ask about time. I guess he is assuming it's the initial conditions.
I feel like he's asking us to compare
The time
the magnetic flux and
the time for it.
the time for it.
Yes, but I mean, when does it reach? When's the first time it reaches maximum flux? This is why I feel it's kind of
Zero.
equals zero.
Yeah.
At maximum flux already. And maximum voltage, we already said in the second question. And it's T equals pi over 2. That's equals 1 per 2 seconds. 1 over 2.
So max flux is at T equals 0?
Yes, when it's
And when
That's at the initial condition then.
Yeah,
it's not always a condition in this case.
I mean, in this case,
Yes. So in this case, when it's like that, you have the maximum field length penetration.
and
I mean,
It's like this.
at 1 second.
What?
And at 1 second, because it's turning this way.
And at 1 second, yes. 1 second is going to be high.
So then you said max voltage is at T equals 1/2 and T equals 3/2, 5/2, yes. So in that case, we would just say
This
that.
function describes it. Starts out like this, right? Flux starts out as a max. That's the move for flux. Starts out like this. Flux is max. Flux is 0. Flux is negative because if your area vector was assumed to be like this, now it's in that direction. The magnetic field is still going out. So your angle is 180. You go back to this, right? That's 0, and you go back to your max.
Dude, you're awesome.
And the voltage.
No, honestly, like if like he taught in these kind of concepts, I think that people would totally understand. Just saying.
And the voltage is maximum change. Because the sine function changes mostly here. Because it's not changing that much. Here's changing more. Here's changing the most. Here's changing least. And so on. So yeah, back to Lenz's law. Lenz's law says that the direction of the current that is induced in a loop, direction of current that's induced inside a loop, its direction is going to be so that it opposes the change inside the flux. I mean, it opposes the change of flux inside the loop. Okay? It's going to oppose the change of flux. Now, why is it related to this? Because when you have an EMF, when you have a current, you have an EMF. If you have an EMF with a closed loop, you have a current. EMF and current inside closed loops, they go together. Okay? So when you have an EMF, the magnitude of that EMF is given by dphi by dt. Okay? The direction of the current that this EMF is going to create is given by Lenz's law. So in this case, if he asks what is the direction of the current when you're going from here to here, the flux through the loop is flux through the loop is going in that direction, right? Initially. As it's moving to 90, what's happening with flux? Increasing or decreasing?
Oh wait, before you said the flux, so we're taking the flux to be the same as the magnetic field. Is that it?
No, the flux is the magnetic field lines that are penetrating an area.
Oh, okay, yeah. So then it's still good.
So the magnetic flux through the loop. So the magnetic field is going that direction. So the magnetic flux. So the flux is in that direction. Yeah, flux is in that direction.
So flux is a scalar quantity then.
A scalar quantity.
Yeah, it is.
Technically.
Wait,
Yes, technically yes.
because
But it's given the direction. I
is,
see what you're saying. Yes, it should technically be a scalar quantity that has direction. I don't know. Actually, I never asked myself this question. That's a good question. Flux is a scalar quantity, but we know it has a direction. I guess this is kind of like a current. Current is not a vector.
Yeah.
But it has two directions, but then again, flux can have multiple directions, so it's not like a current.
So
I don't know. I'm not gonna say this. I'll try to look into that. Why? Okay, so I'll do better terminology. The field lines are going in that direction.
Yeah.
Okay. Since the field lines are going in that direction, as you're moving your loop like that, the flux is going to decrease, right? Because you have less area that's, more area, that's going to be less and less area, right? So the magnetic flux that's going in that, I can't get away from this terminology. The magnetic flux is going inertially in that direction. The magnetic flux is decreasing, right? So now your loop is going to want the magnetic flux to stay the same.
Okay.
For it to stay the same, since it's decreasing, it has to generate a flux in the same direction. Because it's decreasing.
Okay.
Right?
When you're in the opposite direction.
So we said originally the flux is this big. The magnitude of the flux represents the length of the arrow. Let's use that. As it's moving, it has nothing to do with the direction of this. It's just an illustration. As it's moving, it's decreasing, right? The actual flux, external flux, is decreasing. Your loop wants all the fluxes to be with this magnitude. It's going to generate one here, one here. It's going to generate one in the same direction to keep it from decreasing.
Oh, to bring it back to the.
To bring it back to the original one, yes. So this is the original one. And now it's moving like this. Sorry, it's moving like this, which is decreasing the flux from outside. So it wants to create a current inside it so that the flux is in the same direction. So that the flux is in the same magnitude and direction.
So in terms of say the diagram that we have, how in terms of the diagram that we have, the triangle that we have, how are we going to indicate the direction of say induced current that?
Flux. This is the magnetic flux. Increasing. You want to generate one that keeps it the same. Sorry, decreasing. This is decreasing. You want to generate one that keeps it the same, which is going to be direction, right? It's going to be a flux. It's going to be a magnetic field, right?
Yeah.
It means should be the direction of current.
See, this is another notation that kind of like gets me because usually we're told that for the right hand group, the direction of current
IL cross D.
Then the point finger denotes the direction of
that's it. Mu naught I to pi D. Mu naught I over 2 pi D.
Okay. So again, with the induced current, you said the flux is outward, and then so that means we go counterclockwise.
Yes, in that direction. I don't know.
What equation is that?
Which one?
So like the cross product you're doing right now.
This is just to find the direction of. So, if you have a loop that has a magnetic field that's creating a magnetic field in a certain direction, you want to find the current that's inside it, the direction of the current that's inside it. Use something like vice-versa law. It's the same thing. These are all related. It's the same vice-versa law because vice-versa law tells you if you have a current I, it's going to give you mu naught I over 2 pi d, right? B is going to give you mu naught I over 2 pi d. And the direction of that, if your current is in that direction, this is your magnetic field. If your current is in that direction, this is your magnetic field, right? So this direction or in that direction. In our case, we know that the B field is in that direction. Therefore, I is in that direction.
I thought the B field is always represented by fingers.
The thing.
That's why I was asking. What? Like,
it's only if A cross B gives you C. A is always represented by these fingers. These. I don't know which one you use.
I use a gun.
Gun. Okay.
It's just a lot easier.
I'm so confused about that. Wait, A.
I thought A was with this finger.
A cross A should be the same thing. Right. X cross Y gives you Z. X cross Y gives you Z. X. X, Y, Z. X cross Y gives you Z. Which one you said?
This for A.
Yeah.
A, this for B, and this for C.
X cross Y gives you C. Yes, it's C.
Okay. Now, how do you do the other way? Just the hand.
The what?
How what would your A be?
Curving?
Yeah.
A towards B gives you C. Okay. So X, because X, I mean, X hat cross, this is why I use these. Y hat is always going to give you Z hat. The direction of that axis cross this axis is going to give you Z hat axis. So X cross Y gives you Z. This is out of page. So if you're ever confused on test or something, you forgot the right hand rule, just do this. These axes are standard axes. Don't draw a left axis because they're you can draw this Z inward. That's not going to work.
You could. I mean, technically in
But then-
geometry they do the Z this way, right?
No, come to me, see, point toward.
Yeah,
Z
that's what I
this
said.
way.
Yeah, there you go.
This is your X though.
Yeah.
This is your Y.
Okay.
Still satisfies it.
Oh yeah, you just flip this. thing.
X cross Y. X cross Y gives you Z. X cross
So then why is it that, say,
It just
for
makes it harder for you to
example,
go like this.
you know, for example, for unit vectors, if you cross them, instead of say, if you say, no, I cross J equals K, right? For unit vector.
Y cross J.
But then if you flip it around as J cross R, you get negative K. So that's like my concern here that, say, for example, for tau, for the top, right, which is R cross F, right? If I said F cross R,
Negative tau.
negative tau.
Yes.
So exactly my question is, in terms of using the right hand rule, I feel like the right hand rule, I mean, it works for some people who like know how it works, but kind of getting the orientation of, okay, which finger should I use for my R, or which finger should I use for my F, so that I can get the right direction for the ball.
You're asking about why,
I feel like my question is, what's the proper rotation of, say, the fingers to actually get the right direction for the ball?
the first cross the second gives you the result.
Oh,
First cross the second gives you a result. Okay, in this case, this is I, J, this is K.
Yeah.
First cross the second gives you K.
Oh.
So I cross J gives you K. The other one is J cross I. J cross I gives you negative K, right? J cross I gives you negative K. Is this J in the direction of Y? L in the direction of X is from it out of the board gives you negative K.
So for the magnetic force IL cross V, IL,
L.
we
L
assume
right
they're
here.
in the same direction, right?
Yes, I is the direction of L.
Okay.
I is not a vector. L is actually the vector that we use.
Yeah, L is a vector.
L is defining a vector of length that is in the direction of the vector. As its formal definition.
How you were explaining, go on. Yes. Yes, so we can't use the gun rule in this thing?
We can.
Oh.
Okay, so second rule for Weissenberg's law, this is basically Weissenberg's law. First, we'll do simple Weissenberg's law. What is the basic formula for Weissenberg's? Does he give you that on the exam?
Yeah, mu not I over 2 pi r.
No, that's the one we derived from. Yes, it's the one with differentials. Hold on, I'll show you. Let's see if someone's saying something on the chat. No, maybe not. Here. Yes, Dominic is here.
So what's going on?
Yeah, Dominic. Is that Bards? Is that how you spell Bards?
Wait, can he hear you?
I think so.
That's pretty cool. Hi, Basil.
Since you're mentioning me, this is I'm just gonna put it on the board. Let's snake
I
him.
mean, I'm gonna come too, but I'm not here. I didn't know like you could. That's why I would prefer coming.
Okay, this is Bias-Savart's law. This is the basic form of Bias-Savart's law. See, it has a cross product. The actual one has a cross product. So the direction is determined by cross product. So the cross product is between L. This is terrible notation, R hat. This is a unit vector in the direction of R. Okay. So if you have this wire carrying a current I in that direction, okay, your L is going to be in that direction, right? L in that direction, because that in the same direction of current. If you try to find the magnetic field at this point P, this is going to be your R. This is your R, right? This is what you apply into this is the raw form. I just call it the raw form. The actual form that we use, we got over 2 pi. This R is the same as this R, okay? Actually, in that case, this shouldn't be on the phrase. So, mu naught I over 2 pi R, okay? R is this R, right? Originally, before the integral, it was a vector. It's because of the simplifications that we did. So it's this vector that's pointing from here to here. If you want to find the magnetic field at this point with the gun rule, it's going to be L cross R gives you B. So it's L. Is that what you do? X, Y, yes. So it's going to be L cross R.
Oh, that's why.
Gives you L cross R gives you B out of the board, which is consistent with the other one.
So in the direction cross.
Yeah. R is going to be the direction from the wire to the point. From the wire to the point. If your point was here, this is your R.
That's
smaller.
That's VOCR.
Yeah, that's Bias-Savart's the basic one, the one that we don't really apply. This is the Bias-Savart's that we use this one. I think they show you the integral in the pre-lectures. Not here. In the pre-lectures, they show you the integral. They just integrate this across an entire wire of infinite length and make that fast.
Yeah, so I just had a question. I already did this problem. So the voltage drop across this is equal to the voltage drop
Yes,
across the
the other two, yeah.
Because they're all parallel?
Yes.
Alright, cool.
Okay. Whew. Any questions? Anything else?
Are you free anytime before the exam in case I have a question?
Tomorrow,
Like right before it?
I am working at the ARC from 12 to
Wait, you're a tutor for
1 to
physics?
3. No, for DC.
Oh, okay. I'm gonna come start seeing. Am I allowed
I'll direct
to
you to the physics table, but okay. No, if you have any questions, that's fine, I can answer.
Okay.
So, from
I mean, I went today and
1 to 3.
I'm not gonna lie, they suck.
See, the thing is, it's not that they suck. It's that I mean, the reason.
I guess you understand it much better.
No, the thing is that I'm close with your class, so I follow your class way more than they do. So the tutors do physics 1, physics 2, physics 3, and a bunch of other physics courses. For physics, I just do physics 2. And if someone comes and asks about an ECE course, and an ECE 2, I'm not going to answer it like this. I'm going to answer your questions. Exactly, college.
So I guess I thought they sucked because I was used to you. So.
Oh.
Well, I mean, I understand, like, you know, what you're doing. 2 of them just told me to, like, because I told them I have a review session tonight. So, like, yeah, 2 of them are like, yeah, we don't know how to do this, just wait for your essay. They literally said that and left, like, once I had to leave. And I was like, all right.
I thought you had to be
Oh, yeah.
a graduate student to be a tutor at
Yeah.
Isn't that how it works? Like you have to be a graduate student to be a tutor. So how do you use it? What?
Yeah.
Oh.
Are you good, Dominic?
So this is to the left.
Oh, Dominic, you're not even here. Why'd you leave us?
All right, so B.
Why'd you leave us, Dominic?
That's lefty. Oh, yeah. Why am I doing? I'm lefty. That's what.
Okay.
That's weird.
I'm ending.
So I was like,
So I want like apply to be a tutor.